So, welcome to the first exercise session for the course Advances in Public Economics in a Political Economy. So, in today's exercise session, we will talk about optimal taxation and we will talk about optimal taxation of commodities, as for instance, goods, and about taxation of income. Yeah, there will be two exercises, and yeah, this is what we will be doing today. So, let us start with exercise number one, which is about the optimal commodity taxation in the many-person Ramsey tax model. So we have an economy with two consumers and two consumption goods, where we denote the amounts of the goods by X1 and X2. There will be labor in the model, so the consumer can work to get income, and we denote the labor by small l. Then the consumer, basically we have two consumers. So consumer A will have a utility function given by this expression here. And as you can see, the consumer is getting strictly positive utility from consumption of both of the goods. And he suffers if he conducts labor. Yeah, so he suffers if he provides labor, if he supplies labor. And it's strictly convex costs of labor that we have here in the utility function. And for consumer B, we basically have the same. So production is kind of linear. So we have a constant return to scale. So each unit labor which is supplied produces one amount of the particular good. We assume that production is competitive, such that the price of each of the goods is equivalent to the marginal cost of production, which is here the marginal cost of labor, which is denoted by W, and W is normalized to 1 here. Yeah, such that what we have is that the prices of the goods are equivalent to 1. We further assume that the consumers have no labor income. Yeah, so basically the labor income is the total income that the consumer has. So there is also a government, and the government has an objective which is given by maximizing aggregate welfare in this economy. And in order to do this, or not in order to do this, but the objective of the government is to raise kind of capital T units of labor, for instance, for building streets or whatever you can think of. And we make a kind of a parameter restriction here with respect to capital T, which will be necessary such that we get a unique solution, not a unique solution, but we get a kind of not a corner solution. So as a consequence, the government needs capital T units of tax revenue. And in order to raise this revenue, the government is going to impose linear taxes on the goods which are in the economy. And we denote the taxes by T1 and T2. So T1 refers to the unit tax on good 1, and T2 refers to the unit tax of T2 of good 2. And by Q, we denote the vector of post-tax prices. Yeah, so basically the price of the good plus the taxes that what we have on the particular good. So in sub-exercise A, we are asked to find the consumer's demand function and to derive the indirect utility function. Okay, so this is a straightforward exercise, which is basically done by conducting analysis. So we are going to solve the optimization problems of the consumers. Good. So let's start with consumer one, and I will immediately jump to the Lagrangian function of this consumer. So this consumer is maximizing or has the following optimization problem. He is, sorry, let me make the pen a little bit smaller. So the consumer is maximizing. So what is he maximizing? He's maximizing the Lagrangian of him, which is LA. And with respect to what? So with respect to the amount of good 1 that he's consuming, the amount of good 2 that he's consuming, and the labor that he's supplying. And there will be a kind of a Lagrange parameter here for he's maximizing over those parameters. So it's he's maximizing over x1a, x2a, and LA and lambda a. And what is he maximizing? So he's maximizing his utility. So 2 times log, so the natural log of x1a plus the log of x2a minus, so we'll continue down here, so minus 1/2 times the labor that he supplied, and yeah, put this in parentheses to not get confused by the a here, so this by the power of 2. And then we have the Lagrange scalar here, so lambda a times, then what we have is basically the income minus the expenditure. So LA is the income. So always think of LA times 1 here, which is then the amount of labor supplied, times the wage that he's receiving, which is then his total income. So LA minus Q1. So this is the total price that the consumer is paying for good 1. So X1A minus Q2 times X2A. Okay, so this is the optimization problem of consumer A. Then we basically have the same thing for consumer B. So we have max X1B, X2B, LB, and lambda B. Then we have the Lagrangian function for this consumer, which is X1B, X2B, LB, lambda B, and then it's the utility function, which is for consumer B given by the log of X1B plus the log of X2B. Then we subtract from this his costs of labor, which is 1/2 LB by the power of 2. And to this we add his kind of constraint. Yeah, so this is lambda B. Multiply this with his income, which is LB, minus his expenditure for the goods. So Q1 times X1B minus Q2 times X2B. Okay, so those are the optimization problems of the firms. And since this is really kind of standard, I will skip the derivations of this. So what you do is you derive the first order conditions, and then you solve for the endogenous variables, and you will end up with the following solution, which I will add here. 1 second. Yeah, so the solution will be given by the following. So we have X1A star, and this will only depend on the post-tax price of good 1, and this is equivalent to 2 divided by square root of 3 times the post-tax price of good 1. So this is the solution for good 1 for consumer A. Then we have the same thing for the second good. So with respect to consumer A, so the solution for the second good is given by the following. It's given by 1 divided by square root of 3 times Q2. Okay, so those are the solutions for consumer A. Then we have the solutions for consumer B. Let me just write it down here real quick. And they are given by 1 divided by square root of 2 times Q1 for the first good, and 1 divided by square root of 2 times Q2 for the second good. And they're equivalent because the impact of both goods on the utility function is equivalent here. Yeah. So the only difference is given by the different post-tax prices. And as you can see, all the demand functions for the goods here are strictly decreasing in the post-tax price, obviously, because the higher the The higher the post-tax price, the higher the opportunity costs if you consume this good, therefore the demand is decreasing here. And given those expressions here, we can simply, sorry, I missed one thing. So those are the demand functions for the goods. And the next thing that we can derive are basically the optimal labor supplies for the consumers. So the optimal labor supply for consumer A, so L, A star, is equivalent to square root of 3. And the optimal labor supply of firm B, consumer B, sorry, is square root of 2. Yes, so those are the optimal labor supplies in equilibrium. Now, given those expressions here, the next thing that we can do is that we can derive the indirect utility functions, which I will round up to 2 places after the decimal point because there will be a number there. So you simply plug in those expressions into the utility functions for the corresponding consumer, and then you end up with the following expressions. So we'll try to write it down here. So the indirect utility function for consumer A depends then only on the post-tax prices Q1 and Q2, and it's equivalent by minus 1.76 minus 2 times log of Q1 minus log of Q2. Okay, hope you can still read it here. So this is minus 2 times the log of Q1 minus log of Q2. The same thing for for consumer B. So the indirect utility function of consumer B is given by minus 1.69 minus log of Q1 minus log of Q2. Okay, and obviously the indirect utility functions are strictly decreasing in the post-tax prices because obviously then they can consume less of the goods. Yes, that's basically the solution for this sub-exercise.